Okay, good morning, guys. Um, we have quite a bit to talk about today, so I'm just going to jump right in if you don't mind. I know you're going to hear a bit of a loud whirring noise in the background as my computer struggles to process the video from my last class, but it will stop soon. This is, of course, MAC2311.0H1, and today is the 15th of January. Some announcements. I need from you today your honors projects and your student teaching. So today is the deadline for honors project topics and student teaching section choices. And a lot of folks have sent me stuff already. So here's what I have for the student teaching so far. I think I still need Jonathan's, Jacob's, and one of our Ben's student teaching ideas. I think Kieran and Ben Samuel are going to co-teach 5.1. And then there was one other co-teaching thing, I think. Yeah. Tahara and Haley are going to co-teach 3.1. And these are getting close. So we're going to need to talk about these 3.1 things soon. Now, I did just notice that the default day 1 week before the lecture for 3.1 happens to be next Monday, and next Monday is Dr. King's birthday. So in honor of all he did, the college is closed on the 18th. So we're going to have to move this meeting. So Tahara and Haley, I need you guys to get your lecture materials prepped over the weekend. And then we're going to move this rehearsal day to Tuesday of next week, if that's okay with you. Are both Haley and Tahara here?
I'm here. What time on Tuesday?
So I have a normal office hour on Tuesdays from 11 to 12. Are you free during that hour?
Yes, that's fine.
All right, so let's plan to do that then during my 11 to 12 office hour on Tuesday, the 19th. So I'll move this. Is Tahara here? Not yet. Let's see. Oh, here we go. Participants. Yeah, maybe not yet. Okay. So, Haley, have you guys swapped contact information? Are you able to communicate with Tahara?
Yes, we have.
Okay. If you wouldn't mind sending her a text, letting her know that we're moving this rehearsal to 11 a.m. on Tuesday, January 19th, that's next Tuesday, and make sure that she's available to come at that time. I'm also free after 2 p.m. on that day, so if we don't get it all done between 11 and 12, that is a normal office hour, so I may have other students coming in, then we can also meet later in the day. But we need to make sure that that meeting takes place, and I need you guys to have your lecture materials ready to go, or at least very, very close to ready to go, because this is supposed to be our rehearsal. Um, Now, I've gotten emails from a few people asking to do a few specific sections, and I'll be filtering through and responding to those emails later today. But please make sure you send me what you want to do. And if the thing you wanted to do, if you've already emailed me or if you've been thinking about it, is one of these, then I'm going to need you to make a different decision or contact the person who's already claimed that and see if they want to co-teach it with you. These are due by the end of the day today. I need both of these sorted out by the end of the day. Same goes for honors project ideas. A few people have emailed me. I haven't started filtering those out, but I haven't had any issues. I think somebody claimed the soup can topic. We've had somebody doing the video game series Halo's impact on like water modeling physics. And I think I had one other specific request. So make sure you get these things to me today. Another announcement here. My normal office hour today is going to be moved to 4 to 5 p.m. I have an appointment to go look at a house at 2, so I won't be able to do my normal 1 to 2 office hour. And then the other obvious announcement is that there will be no class next Monday. On 18/21 in honor of Dr. Human's birthday. Okay, so those are all my announcement-y things. Please make sure you get this information to me today. Really, really important. And then if your lecture is coming up soon, make sure that you've begun prepping your materials. Make sure that you're reading the section, you're getting ready. Make sure that you are aware of our meeting date. So everybody who's emailed me, I sent back these meeting dates. Please, please, please put those in your calendar. Give yourself a few warning notifications and maybe an alarm 10 minutes before, just so we were able to make sure everything goes off smoothly. I think that's all of this stuff. So the actual lecture material for today, we're going to look at more continuity stuff. Which is section 2.5. And we're going to look at limits as x goes to plus or minus infinity, which is section 2.6.
Mr. Foster, Professor Foster Grammar.
Yeah.
Yeah, I was just wondering, like for the class teaching, you had like the graph, the table.
Yeah.
Could you like show it again?
Sure.
Yeah, I saw that the rehearsal is the 17th of February, right? For my.
Oh, are these backwards? I might have.
Yeah, I think yeah.
I'm sorry. Thank you. Let me double check the syllabus and make sure everything is as it should be here. So you guys are where section 2, here you are. So let me come down here, linear approximation. I probably just typed them in backwards, but just to be sure. Approximation, that's going to be the Wednesday of this week, which is, what is this? What do I have? 17th of February for the rehearsal. When indeed, yeah, okay, so these are backwards. That's
all right, got it.
Okay, thank you. Okay, so let's come back to here and I'm going to continue with what we were talking about. The precise definition of a limit stuff, I think I'm going to let that lie. I think we've covered enough of that. I'll do 1 or 2 more problems with it next week, and I'll put a problem, a small portion of your problem set next week on section 2.4. But for the purposes of the class, to get you guys really understanding and working with calculus, it's everything else in chapter 2 that's more important. 2.4 is great for really understanding what's going on at a deep level, but it's not useful for calculation. And our main goal in this class is to get you guys understanding and performing these calculations accurately and quickly. So I'm not going to dwell on that any more than we need to, but I will show you a couple more examples next week, and I will include a few problems from that section in next week's problem set. But I want to talk more about continuity. You remember last time we finished last time by showing that the function f of x defined piecewise as x squared minus 3x over x squared minus 9 if x is different from 3, and 1 if x is equal to 3 is not continuous. And I'm going to abbreviate the word continuous in the future, CTS, because it takes a long time to write. is not continuous at x equals 3 by showing that the limit as x approaches 3 of f of x, which we calculated by simplifying this part to x over x plus 3, this was 1/2, which is not equal to f of 3 itself, which is defined to be 1. Right? So that's an indirect violation of the definition of continuity, which says, f of x is continuous at 3 if the limit as x approaches 3 of f of x is equal to f of 3. And since this is not equal to this, we know that the function isn't continuous there. I asked you guys to draw the graph, remember? So the last thing I asked us to do yesterday was to sketch the graph of this function. I want to show you what that graph looks like, because we're going to talk about a few different kinds of discontinuities. So here's what the graph of this function looks like. Okay. We have a vertical asymptote at -3. We go through the origin. If you plug in 0 to this expression, you find f of 0 is equal to 0. So our only x-intercept is also our y-intercept. We have a horizontal asymptote. It's the line y equals 1. And yeah, we have this vertical asymptote over here at -3. This sort of discontinuity right here this sort of shit is called a removable discontinuity. We call it removable because if we were to just redefine the height of this dot so that it filled in this hole, the discontinuity would go away. All of a sudden, the limit as x approaches 3 of f of x would be equal to f of 3. In other words, if I just come back here and change this definition, this 1 to a 1/2, that would fix things. The discontinuity over here is called an infinite discontinuity. So what I want to show you next is kind of how to classify continuities, or classify discontinuities rather, and just give you like an example of each. And that's going to lead us to talking about limits at infinity. Let's see, and we might want to talk about that. Yeah. Okay. So classifying discontinuities. I'm just going to draw a picture for you here, and then I'll give you more specific definitions. Here are some different types of discontinuities we can run into. I'll call this A, I'll call this B, and I'll call this C over here. If this is the graph, y equals f of x, and this is my x-axis, then the function f has discontinuities. The function f of x is not continuous at x equals a, x equals b, or x equals c. And the specific things that go wrong at x equals a, we have what's called a jump discontinuity. And I could fill one of these in, I really should, yeah. We have a jump discontinuity. A jump discontinuity is anywhere the limit from the left is not equal to the limit from the right, but both are finite. Both one-sided limits exist. And are finite. All right, so the limit as x approaches a from the left, that's this y value. The limit as x approaches a from the right, that's this y value. Certainly both of those one-sided limits exist and are finite. Right, this one would be whatever that y value is. The left one would be whatever this y value is, but they're not equal to each other. So the graph has this jump, right? It's a disconnected piece there. And there's a jump from the one portion of the graph to the other. The discontinuity at B is also a jump, right? I guess, yeah, this is okay here. So 2 at x equals B, we have another kind of jump discontinuity. I guess really I need to, if I'm going to have all of the different types of discontinuities in here, I'm going to need to add one more. Let me add the one more over here. Let me say here, I've got like just a hole like that. And then we've got a filled in bit down here, and I'll call this D. Yeah, sorry about this. So jump discontinuities can have the hole filled in at one side, can be open at both sides, and then have a hole up here, right? A and B are both what we would call jump discontinuities because the graph kind of approaches one value from the left and another value from the right. At x equals C, we have what's called an infinite discontinuity. This is anytime one of the one-sided limits is infinite. So here as x tends to C from the left, f of x is going to plus infinity. And as x tends to C from the right, f of x is going to negative infinity. Even if one side of this wasn't infinite, like if we just went to plus infinity over here, but we had some finite limiting behavior on the right, we would still call that an infinite discontinuity. And then over here at D, x equals D, here I'll just go like this. X equals D, we have a removable discontinuity, which is the type that we discussed before. This is where the limit x approaches d exists, but is not equal to f of d, right? So the filled in hole there, if you just move this dot back up to the area part of this hole, then that would get rid of the discontinuity. That's what a removable discontinuity is. So we've got these three types. They're jump discontinuities, infinite discontinuities, and removable discontinuities. And jump discontinuities can look like different things, but the main idea to identify a jump is that you've got a piece of the graph over here and a piece of the graph over here, and they just don't meet up. It doesn't really matter what happens here, right? You've got a piece of the graph here and a piece of the graph here, and they just don't meet up. Infinite discontinuity, that's anywhere you've got a vertical asymptote, right? Anywhere the function blows up to plus infinity or explodes down to minus infinity. And a removable discontinuity is one where you could just redefine the value of the function at that point to make the discontinuity go away. Okay. So these are the types of discontinuities that we will encounter. There's also this thing called a one-sided, being continuous from one side. So I want to kind of draw you a picture for that and show you what that looks like. First, I'll give just a second here. Anybody who's writing. We have a homework problem that talks about being continuous from the left or continuous from the right, and we need to see what that means. One-sided continuity. If f of x is not continuous at x equals a, but the limit as x approaches a from the left of f of x is equal to f of a, then we say that f of x is left continuous at x equals a, or if lim x to a from the right of f of x is equal to f of a, then we say f of x is right continuous, again, at x equals a. So one-sided continuity is something that we only really talk about if the function isn't overall continuous. If you are both left and right continuous at a, then you are just straight up continuous at a, and it wouldn't make sense to talk about left and right separately. An example here. Again, these are not things that arise naturally as like rational functions or anything like that. But call this -1. Call this +1. Call this height right here just 1. We'll call this 2. Call this down here -1. If this is the graph again of f of x, and here's my x-axis, then this function satisfies lim x to -1 from the left of f of x, that's equal to 1, and f of -1 is equal to 1. So this function is left continuous. At x equals -1. It's not continuous there, there's a jump, but it is left continuous there, because as you sneak up from the left, you do get the same thing as the function value. Also, the limit as x approaches +1 from the right of f of x, that's equal to 2, and f of 1 itself is equal to 2. So here I'd say f of x is right continuous at x equals +1. Yeah, so this is what one-sided continuity is. This is not going to be hugely important in the course, but it gives us an opportunity to just feel around a little bit deeper with these concepts. So I want to show you what this means. And there's, I think, one homework problem that I gave you that addresses this one-sided stuff. Just to be clear, f of x is not continuous at 1 or at -1, right? There's a jump discontinuity here. There's a jump discontinuity here. But over here, we are left continuous, and over here, we are right continuous. So it's the idea that these filled in holes are correct for at least one part of the graph, right? If the filled in point was up here, then we would be neither left nor right continuous at -1. And if this filled in point was like down here, then we would be neither left nor right continuous at +1. If the filled in point here was moved down to here, then we would be left continuous at 1. And if you move this filled in point down here, then we would be right continuous at -1. Does that make sense? Okay. I think we've talked enough about continuity. I don't want to beat you guys to death a whole lot more. There was one other kind of interesting pathological example I asked you to look at. Remember that function e of x, the modified Dirichlet function? That thing is continuous at 0. Even though it's wildly misbehaved, the limit as x approaches 0 for that function does exist. That was the, I said there's one and only one number a such that that limit exists. That was 0, right? And that function, despite being discontinuous everywhere else, is actually continuous at 0. Cool fact, weird fact, but true. Else about continuity. Oh yeah, one other thing related to continuity. There's a theorem. A theorem called the intermediate value theorem. This is sometimes abbreviated IVT. And it says if f of x is continuous on the closed interval a to b, then for any number, how do I say this? For any number c, oh no, I don't want to use the letter c here. I'll use the notation your book uses. For any number x between, there we go, n. All right, then for any number n between f of a and f of b, there exists a number C between A and B such that f of C is equal to n. This is not that same capital N as we have over there. This says that the image of a connected set under a continuous function is another connected set. Another way to say that is you cannot go with a continuous function, you cannot go from beneath some point, call this A, call this over here B, some N here. If f of A is down here, f of B is up here, so this is the point A comma f of A. This is the point B comma f of B. What the intermediate value theorem says is you cannot go from below this line to above this line without crossing that line if your function is continuous. So no matter how you try to connect these two, there will be some number C in between A and B where your function takes the value n, right? So this is the point C comma f of C, and f of C is equal to n. Right? You cannot go from below this line to above this line, or vice versa, from above to below, without crossing that line, unless you have a discontinuity. So it's the fact that f is continuous that makes this true. Another way of saying this is that the image or the range associated with a continuous function is an interval. So continuous functions map intervals to intervals. Here, the image of the interval AB is the interval f of A to f of B, and it is a continuous unbroken interval. You cannot go from down here to up here without hitting everything in between. Right, so here's the number n between f of A and f of B. And here's the number C guaranteed to exist by the theorem where my function is equal to n. And the theorem just says you can't go from below the blue line to above the blue line without crossing the blue line. That's all. Surprisingly useful theorem. One of the things you may remember from your pre-calculus classes is all the work you did factoring polynomials. You guys remember that? You got like your rational roots theorem, you got your Descartes' law of signs, you got a bunch of weird tricks in synthetic and long division that you use to try and find roots of polynomials. Well, it's hard, right? It's hard to find the roots of polynomials, but you know polynomials are continuous functions. We proved that, right? We proved that the limit of any polynomial is equal to what you get when you just plug in the number, which is the same thing as saying that every polynomial is continuous on all real numbers. So one way to show that there is a root of a polynomial is to show that that polynomial goes from being negative to positive. The only way to go from being negative to positive is to cross through the x-axis. So these are classic problems. I can show that, for example, 4x, what is this? Let's do it. 4x cubed minus 6x squared plus 3x minus 2 equals 0 has a root somewhere between 1 and 2. Show that the polynomial p of x equals 4x cubed minus 6x squared plus 3x minus 2 has a root somewhere between x equals 1 and x equals 2. This is a degree 3 polynomial. It's not necessarily easy to factor. I think I might see a way to factor this thing, but it's not an easy thing to factor in general, right? Degree 3 polynomials can be pretty hard to work with. Once you get to degree 5 or higher, you're fucked. Like fucked. Like there is no way to come up with a formula for those roots as a function of the coefficients. If you're lucky, you can find one using the rational roots theorem, but in general, we're pretty screwed. But here, so here's the solution. P of 1 is 4 minus 6 plus 3 minus 2, which is negative 2 plus 3 is positive 1, minus 2 is negative 1. And P of 2, well, that's 4 times 8 minus 6 times 4 plus 3 times 2 minus 2. This is going to take just a second. 4 times 8 is, let's see, 2 times 8 is 16, this is 36. Is that right? 32, sorry, 32 minus 24 plus 6 minus 2. 32 minus 24, that's 8 plus 6 is 14 minus 2 is 12. So since P of 1 is negative 1 and P of 2 is positive 12, I have no idea what happens elsewhere. But since P of 1 is negative 1, which is less than 0, and P of 2 is positive 12, which is bigger than 0, and we know P of x is continuous, well, so they've asked us to show, the problem asks us, show that this polynomial has a root somewhere between 1 and 2. So it's in the statement of the problem for us to try and figure out or prove that there must be a root somewhere between 1 and 2. If they hadn't told me that, I wouldn't have a place to get started. So it's true that I need this to get started here. But then the idea is, since P of 1 is smaller than 0 and P of 2 is bigger than 0, since P of x is continuous on the interval 1, 2, we know that P of x must attain every value between P of 1 equals negative 1 and P of 2 equals 12. In particular, there is some C between 1 and 2 such that P of C equals 0, right? Because 0 is between negative 1 and 12. So because my function goes from being negative over here at 1 to being positive over here at 12, it had to cross the x-axis somewhere in between. That's the idea. You can try to sort of draw a picture here. I don't have any idea what this function looks like, so I'm just really just spitballing. But we can try to draw a picture of some sort. I'm going to zoom way in on my x-axis. So here's 1, here's 2. I know that P of 1 is negative 1. So maybe actually I'm going to fill this in. I'll put my label over here. P of 1 is negative 1. And P of 2 I know is way up here at 12. All right, this is 1, comma, -1. This is 2, comma, 12. So somewhere in between here, I have no idea what sort of crazy bullshit is going on either side of this thing. But somewhere in between here, this thing, no matter how hard you try to avoid it, whatever, somewhere in here, it had to cross the x-axis, no matter how hard you try to avoid it. I'm not saying that the graph looks anything like this. I'm just drawing squiggles. But we know we came from down here because P of 1 is -1. And we know we've got to get up here because P of 2 is 12. And because P of x is a polynomial, its graph has to be continuous. So somewhere between 1 and 2, we crossed that x-axis. That's the game. This theorem does not help us find the root. That's kind of unfortunate, right? That is not something that this theorem will do. It only guarantees the existence of a root. But sometimes that's a victory. Sometimes just showing that something exists is enough to get done what you need to get done. Okay, we need to talk about limits at infinity, because there is a meaningful portion of your homework this week that addresses limits at infinity, and we haven't talked about that shit yet. Good news is this stuff is intimately connected to something you've seen before, horizontal asymptotes. The idea is this. Let me draw for you a picture here. All right, again, I'll call this graph y equals f of x. This blue line right here is the line y equals L. I don't really care what the function does over here. But the line y equals L, I'm drawing as a horizontal asymptote for this function, right? That's what this looks like. It looks like my function is getting closer and closer and closer and closer to that horizontal line as we wander further and further and further to the right. Definition. We say that the limit as x goes to plus infinity of f of x is equal to L if f of x can be made arbitrarily close to L by taking x to be sufficiently large. Meaning if God hands you epsilon, here's the delta epsilon, I'll give you this one. We say lim x to infinity f of x equals L, provided for every positive number epsilon there can be exists a number capital N, no relation to the capital N from the previous theorem. There exists a number capital N such that if, I'll write it like this, if x is bigger than n, then the absolute value of f of x minus L is less than epsilon. They say the same thing, right? We can make f of x arbitrarily close to L, meaning the distance from f of x to L can be made less than epsilon by taking x sufficiently large, by taking x bigger than some number n. So let me come into the picture and try to draw for you the delta epsilon stuff. I'm going to make this blue line a solid line so that I can draw an epsilon window about it using dotted lines without things getting confusing. Maybe here's L plus epsilon. Here's L minus epsilon for some particular value of epsilon. Notice that once I get past this x value right here, once I get past that x value, the graph of f of x is trapped in this epsilon window. So for all x's bigger than capital N, it's true that the distance from f of x to L is less than epsilon. The vertical distance between the solid purple and solid blue is smaller than the width of the dotted blue window and stays like that. So for every x bigger than capital N, f of x is within epsilon of L. These two things say exactly the same thing. The bottom one is the rigorous way to say it. This is how a mathematician would define that limit. There's a third way to do it. We say lim x to infinity f of x equals L if f of x has a horizontal asymptote, has horizontal asymptote y equals L, which it approaches, which f of x approaches as x goes to infinity. All right, to the right. We say, so after up here, we say lim x to infinity f of x equals L if f of x can be made, I left off an E here, didn't I? Can be made arbitrarily close to L by taking x sufficiently large. Is this the one you're asking about, Katie? Can be made. Yeah, sorry, I left off the E. So if the y values along the purple graph get closer and closer and closer and closer to the blue line, y equals L, as you wander further and further and further to the right, that's what we mean to say that the limit as x goes to infinity of f of x is L. The middle guy is your delta epsilon stuff. Here there's actually no delta, just an n and an epsilon. And then the bottom one is sort of the intuitive one, right? This is what everybody thinks of. You know, if a horizontal asymptote is something you learned about in your algebra classes, where the y values on the function get closer and closer and closer and closer and closer to some particular number as x gets bigger and bigger and bigger and bigger and bigger as you walk further and further and further to the right. That's what you learned a horizontal asymptote to be back in your algebra classes, and now we're just rephrasing that. We're saying having a horizontal asymptote y equals L is the same thing as saying the limit as x goes to infinity of f of x is L. It means that the function approaches that y value as x gets bigger and bigger. Mathematicians like the middle statement because the middle statement is something that you can use to prove things because it allows you to get very quantitative. There are a bunch of really important horizontal asymptotes, a bunch of really important limits at infinity that I want to discuss. But first well, no, okay, let's do it. So some specific ones that you hopefully are familiar with. Some important limits at infinity. Remember what the inverse tangent function looks like. Arctan, or inverse tangent function. This is one of my favorite functions, and we will talk about this guy a lot in this class. He has a horizontal asymptote up there and another one down here. He has two horizontal asymptotes. How is that possible? Well, one of them he approaches on this side, and the other one he approaches on this side. So this is the graph y equals inverse tangent of x. This line up here is pi over 2. This one down here is negative pi over 2. So we say the limit as x goes to infinity of the inverse tangent function of x, this is positive pi over 2. And the limit as x goes to negative infinity of the inverse tangent of x, this is negative pi over 2. Another important guy like this, the natural exponential. E to the x and its reciprocal, e to the negative x. So another graph you really should know, but in case you don't, here it is. This is y equals e to the x. It looks like this. The limit as x goes to negative infinity of e to the x, this is 0. The limit as x goes to positive infinity isn't interesting here. As x wanders off to positive infinity, e to the x, he just gets bigger and bigger and bigger. We would say this is plus infinity. And then his reciprocal, e to the negative x, is geometrically related to the original just by flipping him around horizontally. And that's a transformations of graph things. You swap x for negative x, you get a horizontal reflection, remember? So the limit as x goes to positive infinity on e to the negative x, that's 0. And the limit as x goes to negative infinity, e to the negative x, this one's boring, this is plus infinity. All right, so 3 very important functions. There is this intuitive idea that like 1 over infinity should be equal to 0. And I'm going to put this in quote bunnies. Right? 1 over infinity equals 0. By this, I mean, I don't take responsibility for this, not rigorous, but useful. The way you understand this is the reciprocal of a huge number is something close to 0. Something very close to 0. And the e to the x, e to the negative x thing is a great way to understand that, because e to the negative x is 1 over e to the x. So seeing this in action, the limit as x goes to infinity of e to the negative x, you could argue this by saying, okay, well, it's the limit as x goes to infinity of 1 over e to the x. And then by my limit laws, that should be 1 over the limit as x goes to infinity of e to the x. And you know that e to the x itself, as x gets big. So this is like 1 over infinity, which should be 0. I will accept this sort of logic. All right, you can use logic like this on exams and homework, on study guides, and I'll be perfectly happy with it. The intuitive idea that 1 over infinity is 0 is totally fine by me. In fact, I can make it a little bit more useful in the context of power functions. So you know what the graph of 1 over x looks like. Looks like this. And over here, it looks like this. There is a vertical asymptote at 0, but I'm not really interested in that right now. Here, the limit as x goes to infinity of 1 over x, that's 0, right? As I wander out further and further along this graph to the right, my y values get closer and closer to 0. And the limit as x goes to negative infinity of 1 over x, that's 0 as well. As I wander out further and further to the left on this graph, my y values get closer and closer to 0. What about 1 over x squared? Again, these are all graphs you should know. Here's what 1 over x squared looks like. He also has this horizontal asymptote y equals 0 that he approaches on both sides. So here I would say that the limit as x goes to infinity of 1 over x squared, that's 0. And the limit as x goes to negative infinity, 1 over x squared, that's also 0. Right? Because as I wander out to the left or the right on either of these graphs, my y values are getting closer and closer to 0. You can imagine yourself as a little dude walking along these graphs. As you go further and further and further to the right, your y values get closer and closer to 0. As you go further and further and further to the left, your y values get closer to 0. That's these two statements. And the same thing is true on this guy. As you go further and further and further to the right, you know, this just gets closer and closer to that horizontal asymptote. So your y values will be getting closer and closer to 0. That's the statement. And as you wander further and further off to the left, again, your y values get closer and closer to 0. You notice a pattern, right? There's a clear pattern here. When mathematicians notice patterns, that means there's a theorem hiding somewhere that needs to be proved. Theorem. For any positive real number r, the limit as x goes to plus infinity of 1 over x to the r is 0. And as long as there are no domain problems, the limit as x goes to negative infinity of 1 over x to the r will be 0 as well. So of course, if r is like 1/2, 1 over the square root of x, I can't talk about the limit as x goes to negative infinity there because that function doesn't have any negative numbers at all in its domain. But as long as the function is defined for the negative real numbers, then going to negative infinity is the same as going to positive infinity. You'll always get 0. And these are your kind of prototypes. This theorem is more useful than it may appear at first, because we can make it apply to lots of functions to which it doesn't necessarily appear to apply at first. So I'm going to show you some examples of that in just a second. First, are there any questions on those limits at infinity so far? Okay. So a quick example here. I would like to calculate the limit as x goes to positive infinity in the rational expression 2x squared minus 3x plus 7 over 5x squared plus 4. I don't know what the graph of this thing looks like. I just made it up. It's not going to be a super easy thing to graph because the top isn't going to factor nicely and the bottom doesn't factor over the real numbers at all. So graphing this is not going to be the path. This theorem, however, we can use this. I need to make some shit like this show up if I'm going to use that theorem. And so far, I don't have any shit like that. But there's this trick. I call it renormalizing. Renormalizing, if you're a fan of physics, is this thing where physicists divide through all their calculations by the speed of light, so that the speed of light becomes 1 in their calculations, and then you can carry out a lot of stuff in that perspective more readily. The renormalization trick is where you divide top and bottom by the fastest growing term. That's what I mean by renormalizing. So let's look at all the terms that exist anywhere in this expression. Upstairs, I have an x squared, an x, and a constant. Downstairs, I have an x squared. So the fastest growing term anywhere in that expression is x squared, right? X squared grows faster than x, grows faster than a constant. So if I want to use my renormalization trick, I need to divide top and bottom by x squared. So that limit is equal to len x to infinity 2x squared minus 3x plus 7, all divided by x squared. I'll write it like times 1 over x squared because it just makes the notation easier. And if I'm going to divide by that upstairs, I have to divide by that downstairs. So I divide top and bottom by the fastest growing term, which is x squared. Now I need to distribute those 1 over x squareds, actually divide the top and bottom by those things. When I do this, 1 over x squared times 2x squared is 2, minus 3x times 1 over x squared is 3 times 1 over x, plus 7 times 1 over x squared is just 7 times 1 over x squared. Nothing to do there. Now downstairs, 5x squared times 1 over x squared, that's 5. Plus 4 times 1 over x squared is just 4 times 1 over x squared. Limit laws. I'm only going to do this once because normally we don't want to use limit laws so verbosely. But here I have lim x to infinity of 2 minus 3 times lim x to infinity 1 over x plus 7 times lim x to infinity 1 over x squared. All divided by lim x to infinity of 5 plus 4 times lim x to infinity 1 over x squared. Now, who can tell me how I use my theorem at this point?
You know that the 1 over x or 1 over x squared is going to equal 0, so you can cross those out.
Good. I would say all three of these pieces are equal to 0 by the theorem. And while my notation choice might not be to cross them out, you've got the exact right idea. They're going to contribute nothing. So I would just write a 0 in for each of those. So this, what about the 2 and the 5? What is the limit as x goes to infinity of the constant function 2? Don't think too hard.
It would be the same thing.
This 2, yeah. The limit of a constant is always that constant. Remember, that's also one of our limit laws. So I'll get 2 minus 3 times 0 plus 7 times 0, all divided by 5 plus 4 times 0. Well, all those zeros are 0. This is just 2 over 5. This is the power of renormalization. Identify the fastest growing term, then divide out top and bottom by that fastest growing term. That will give you some constants and a bunch of stuff that goes to 0. It's good shit. How am I doing on time? All right, I think, wait, what is this? You guys, we got about 15 minutes left. Or no, it's 12:08. We got about 7 minutes left. Okay. I have one other example I'd like to show you with renormalization. Are there any questions about what we did here? Okay. Sometimes the algebra can get a little sticky. If you look at this guy, I would again like to apply my renormalization trick, but it's not immediately clear what the fastest growing term is. Downstairs, the fastest growing term is the x, and upstairs I have an x squared, but it's trapped under a square root. So the fact that this x squared is trapped under a square root means that he's really only contributing to the top growth at about the speed of x. Now, you know, you can't distribute this square root. This was one of the problems from the interview that you all passed to get into this class. You cannot distribute this square root. Square roots are the bane of our existence in algebra. They really don't play nice with addition or subtraction. And since there's this plus going on underneath this square root, we cannot just give the power 1/2 to everybody in there. But because there's an x squared under a square root, I think of him as contributing to the growth at about the same speed an x term outside a square root would. So here I'm going to renormalize again. And this time I'm going to say that the fastest growing term upstairs or downstairs is just x, because the x squared under the square root is like an x, and there's an x downstairs. So I'm going to renormalize by dividing top and bottom by x. So this would look like lim x to infinity square root of 2x squared plus 3 times 1 over x divided by 5x minus 1 times 1 over x. Now here's the funny business. If x is positive, then 1 over x really is the same as the square root of 1 over x squared. Note, if x is negative, then 1 over x is the negative of the square root of 1 over x squared. I'll let you think about why that's true. Not hard to prove. Just straightforward algebra if x is positive. And then in the case where x is negative, you'll have to think a little bit carefully. I'll say this is a consequence this comes from the fact that the square root of x squared isn't x, it's the absolute value of x. And the absolute value of x is negative x if x is less than 0, and positive x if x is greater than or equal to 0. The upshot is, here I'm sending x to positive infinity. So I'm definitely interested in x's which are positive. So the 1 over x upstairs I can rewrite as the square root of 1 over x squared, giving me square root 2x squared plus 3 times square root 1 over x squared. And then downstairs, I still have my 5x minus 1 times 1 over x. Now that the numerator is a square root times a square root, I can combine them. Square roots play nice with multiplication. They just hate addition and subtraction. So the square root of 2x plus 3 times the square root of 1 over x squared is the square root of 2x squared plus 3 times 1 over x squared. You can combine two square roots as long as they're multiplying each other, just like that. And then downstairs, I still have my 5x minus 1 times 1 over x. Is everybody with me so far?
Yeah.
All right. So everything under this note here, it's not relevant for this particular problem. But if I wanted to take the limit of this same function as x goes to negative infinity, then I would need to make use of this. So I just wanted to show you. Now I'm about ready to use my theorem. I will distribute the 1 over x squared under the square root upstairs, and I'll get 2 plus 3 times 1 over x squared. And downstairs, I'll distribute my 1 over x, giving me 5 minus 1 over x. And now I'm not going to write out the step with the limit laws. I'm just going to say that this 1 over x squared piece is going to go to 0. It's not equal to 0, but this goes to 0 as x goes to infinity. And similarly, this piece goes to 0 as x goes to infinity. So I end up with the square root of 2 plus 3 times 0 over 5 minus 0, which is the square root of 2 over 5. So this is right where we have to stop today. We are out of time here, and that's perfect because we've gotten through all the theorems and all the main examples from section 2.6. I want to say one or two quick things before I let you go. So please give me just one more minute or two of your attention here, and then I will set you free, I promise. You should read section 2.6. All right, please read this section. There are way more examples in here than I have enough time to get through. This one is very similar to the one we just did, but they'll have you take a limit at negative infinity of a function like this. And that's something you should practice because it requires use of this note, and it's a little bit tricky. So please read section 2.6 and work through the examples. There's plenty of examples in here that I don't have time to do in class. Read the theorems. The theorems are good, right? We did cover all the theorems, but it's still worth your time to read the theorems. And then, where are we? Yeah, you should look at some of these slightly stranger examples where you have to think about the inside and outside separately, making little substitutions. And where is it? Where is it? Where is it? Yeah, they have some stuff, some discussion here of things you should not do, right? Like infinity minus infinity, this really makes mathematicians squirm. We cannot subtract infinities. We can get into very, very real trouble that way. And the arithmetic of infinities in general is a little bit odd. They have that same picture there that I showed you, the same rigorous definition that I showed you, and they'll talk through some of these other things, which is good. I thought there was one other thing I wanted to say. Oh no, we got to the IVT stuff. Yeah, okay, so you guys don't have to worry about that. So please just read section 2.6 in the textbook and work through the remaining examples there. There's more stuff there than we would ever have time to do in class, but it's very, very worth your time. And please make sure you send me your honors project topic today, and I will email you back saying, yes, that's fine, that sounds great, or I need you to like change this a little bit or come up with some slight variation on that idea. But please email me your honors project ideas and your student teaching section choices. I'd encourage you to take a screenshot here. That way you can see exactly what has already been claimed and what has not been claimed. This isn't entirely up to date. I know I got some emails late yesterday and early today that I haven't added to this, but please take a screenshot here and send me your student teaching decisions if you have not done so yet. That is it. I will let you guys go there. Just grind on that homework. Next week, I'm going to give you some more 2.4 stuff, and then we're going to start moving into the idea of a derivative, which is going to be very exciting. So yeah, that is all. And then Karen, I see that you wanted to talk to me a little bit after class. You're open to hang out. We can chat a little bit. Thomas asked, when will we get confirmation on our research project topics? Thomas, I think I put you down. If I didn't reply to that, where is it here? Yeah, I got you in for the soup can project. I thought I replied to that saying, please go ahead and start reading in the textbook. But if you didn't get that email, I apologize. So yes, you are good to go. The other one that I have confirmed and replied already is Tahara's on Sophie Germain. I know that at least one or two other people have emailed me, and I will be getting back to you guys as soon as I can. Alrighty, I'll ask you guys, if you don't have anything else you need to talk to me about right now, to go ahead and sign out. So Karen and I can chat, but that is it. I will see you all next Monday.
All right, bye. Have a good day.
Take care.
Bye.
Karen, what's up?
Yeah, I just wanted to confirm if this is okay because it's not in the list of topics that you had given us.
Sure.
So I want to work again with Ben Samuel
Okay.
for a group project, and then we were talking about doing something on like the mathematics of mass vaccination. Gosh, that's a hard word to say. So yeah, we wanted to kind of investigate how like what the threshold for herd immunity is. That was kind of essentially the idea that we had, was looking at the mathematics behind how they calculate how to reach herd immunity.
I like that. I think that's a good idea. I would ask that you include a little overview on epidemiology. So herd immunity and vaccination and all of that is really, really good stuff. But I think a lot of people are undereducated on epidemiology in general. Like how would an epidemic spread absent any vaccine or social distancing is something we should talk about in the lead up to talking about that. So I really
Okay.
like that. It's a super relevant topic. I think there's plenty of good mathematics there. Just make sure you give enough background before getting into the specifics of herd immunity and vaccines.
Cool. And as far as the background for that, just like discussing relevant terms, like the historical context of how these things came up, or
Yeah, I think that's sufficient. I would give a little bit of background. I honestly don't know who first started doing a quantitative study of epidemiology, but a little bit of background along those lines would be perfect. So
okay.
like, whoever the big figureheads are in the presumably Renaissance era, when we first started learning about this stuff, tell us who those people are, what research they did, what mathematical models they used. And then you could start talking about modern mathematical models with and without vaccination, with and without herd immunity. And then if you wanted to get specific on exactly what vaccines do to those epidemiological models, I think that would be a really good topic.
Okay, awesome. Thank you.
Cool, of course. All right, I got you guys saved in here. We do need to schedule a check-in. I would like to check in with you guys 3 times throughout the semester. I haven't done this for anybody else yet, but if as soon as you know or you have some rough idea of when you would like to do our first meeting, please send me a message and we can talk through it. I want that first meeting done before spring break if at all possible.
Sure. Is there a certain like threshold of knowledge that you want us to come in to check in one with, or?
I'm pretty loose on this. As long as, you know, I would like you to start doing some research. I'd like you to have some names, some dates, some background information would be good because that stuff can all be gathered very quickly. And then a rough idea of where you want to go with the mathematics. I think as long as we can have those things kind of on paper and starting to crystallize before spring break, we'll be in good shape.
Okay, awesome. Thank you for the confirmation.
Of course. Yeah, of course.
Have a good day.
You too, Karen. I see Haley and Tahara are still here. Did you guys want to talk about something else?
Yes. So I emailed you the other day about my web design issue, right?
Yeah.
Then
What's going on?
yeah, then I paid for the access again, and now they want me it's showing that I haven't done homework 1, but I actually did.
Oh
And
no.
the due date is already passed.
So just so I'm clear, have you paid now twice for WebAssign?
Yes.
That sucks. All right, let's fix this. I think I can get you a refund for one of those, and we should be able to get, I'm gonna have to search here. Should be able to get you refunded for one of those or something like that, and then get the accounts merged. Let me email our Cengage rep. What is this? This is her, right? Okay. Alrighty. I need to pull up the stats from our class. So what happened that you ended up having to pay twice? It just wouldn't let you back into the original one?
Yeah, it let me back in, but it shows me that I have no class in my account.
Weird. Okay, I should be able to copy this to her. So what exactly happened? You paid, did you register at first using the temporary access?
Yes.
And then what happened? So you bought an access code, right? The first access code.
Mm-hmm.
And what happened after you put in the access code?
I bought the access code on their official website directly from the link you gave on Canvas.
Okay, purchase.
Because when I couldn't access my class anymore, I just went back and tried to register for the class again, but it wouldn't let me. So I had to pay again for the access code and then register back for the class.
So the first time you had trouble getting into the class, that was after you paid for the first access code, but before you paid for the second, right? And then you ended up buying another access code to get back in?
So the first, oh, that.
Like, walk me through the timeline. Walk me through exactly what happened when.
So I started using the website with the trial access first. And that's when I did my first homework. And then it shows me that I had 12 days left until I had to pay for the access code. And then before the 12 days passed, they logged me out when I tried to do homework too. That's when I paid for the access code. So I actually paid once, but in my account they doubled the purchase.
So using the temporary access, you completed homework 1, but then you were kicked out early with 12
Yeah.
days left on the trial. At that point, had you already bought an access code, like from the bookstore or something?
No, I bought it directly from their online.
Okay, so following that, so you get in using trial access, you do homework 1, and then you get kicked out early for some reason.
Yeah.
Following that, she paid for and entered an access code purchased from Cengage Online. And did that get you back in?
Yes. Now I registered back for the class, but it says that I haven't done homework 1 and I have a 0 there.
I see. So probably what happened is when you re-registered, let me see if I have you in the class twice. I bet
Okay.
I do. I bet I've got 2 accounts in here with you. How many access codes have you had to pay for? Like, did you have to pay that $100 fee or whatever twice?
Yes, I paid only once, but they doubled the transaction.
Oh, okay. Yep. And I see it right here, right? I've got you in here twice. So what I am going to do, okay, so some error was made and the transaction ended up costing twice what it should have. Student suspects that she paid for 2 access codes. One for the account registered to tsinpara@yahoo.com and another for the account registered to 620132446 sfcollege.edu. I really misspelled registered to one of my students. Run into some issues with registration and for some classes. She actually using temporary access, completed homework 1, but then was kicked out early. 12 days left on the trial. Following that, she paid for and entered an access code for Cengage Online. Some error was made during the purchase. And the transaction code ended up, okay, suspects that paid for 2 access codes, one for the account for this, one for the account for this. Is there any way to merge the 2 accounts in Riverside and refund the cost of the access codes, or at least make it All right. I will send this email to Marlena, our Cengage representative, and hopefully she will get a hold of me and we'll get this fixed.
All right.
In the meantime, are you still able to get into one of these accounts or both of these accounts? What's the situation?
Yeah, I can access the one with my Santa Fe ID.
But you can't access the other one anymore?
I tried, but it wasn't working.
All right. So ideally, we would have you get back into the one that you already completed homework 1 on. So for
Okay.
now, here's what I'll say. Since you've done homework 1 already, don't go back and redo it. If we can't get you back into the original account, I'll just manually give you credit for homework 1 on your new account. So
Okay.
if that's how it works, then I'll try to get them to refund you for the old account. We'll delete the old one and I'll manually give you credit for homework 1. So just go ahead and work homework 2 on whatever account you can, and we'll move forwards once she emails me back.
All right.
All right. I'm
Thank
sorry.
you so much.
Yeah, of course, of course. Hopefully we'll get this fixed soon. Have a good weekend.
You too.